There is another approach that we can take. So provided that you already know the percentage composition and molar mass at the same time, you can bypass a few steps and you can work out the molecular formula directly. And then from there, you can then easily work out the empirical formula, knowing it's just the simplest ratio of the atoms in the formula of the entire compound itself. So I'll take you through this procedure as well in the event that you've got both pieces of information directly. The first step is to determine the mass of each element from the molar mass. So you're working out what fraction of that molar mass is made up by each element. The second step is you're going to divide the mass by the molar mass of each element. So taking the values from the periodic table, which are the relative atomic masses, and dividing your answer in part 1 by the relative atomic mass of each element. And then you go ahead and compare the ratios, and that should give you directly what the molecular formula is. Let's just see how we can do this in the third example. In this case, we've got 3 different elements: compound containing 40.0% carbon, 6.7% hydrogen, and 53.3% oxygen by mass. And we do already know what its molar mass is. Let's go ahead and work out what this molecular formula is directly using the 3 previous steps. So part A is to work out the molecular formula. First step, determine the mass of each element from the molar mass. The molar mass of this compound is up here, 180.156 grams per mole. So we can take the percentage compositions, convert them into just a number, and then multiply that by the molar mass. That'll work out what mass of each element is found in this particular compound. Starting with carbon here, so we've got the mass is equal to the percentage composition, so 40% expressed just as a number is 0.400. We multiply that by the molar mass, and it tells me that 72.1 grams of this compound is made up of carbon, assuming that we have 1 mole of it present. Let's do the same thing for hydrogen. So use its percentage composition, change it into a number, multiply it by the molar mass, and in 1 mole, 12 grams is made up of hydrogen. And finally, with the oxygen, do the same thing, and we find out that 96.0 grams of 1 mole of this compound is oxygen. So you might expect that if you add all these numbers up, it should just equal this molar mass itself. The second step is then to divide these masses that we've determined by the molar mass of each element, which we can get from the periodic table. So for the carbons, I've expressed here that the number of carbons is equal to its mass, which was the 72.1 from the previous slide. We divide it by its molar mass, which is 12.01. And we do that and we end up with an answer very, very close to 6. So I've just rounded it off. The number of hydrogens, again in the same way, take the mass of hydrogen divided by its molar mass, we get an answer equal to 12. And for oxygen, we get an answer of 6. So this tells me exactly how many carbons, hydrogens, and oxygens are found in this particular compound. So we can write that, therefore, as a molecular formula, which is given as C6H12O6. And if we want to convert this and find out what the empirical formula is, it's just expressing this as the simplest ratio. And so what we might find is that these atoms are found in a 1:2:1 ratio, and that, in other words, is the empirical formula, which is given here as CH2O. So far we've seen how the empirical formula and the molecular formula provide some information about a particular compound. Another way of representing formulas is in the form of a structural formula, and this is probably the most important for us when we're looking at hydrocarbons, because it's important we understand how these specific atoms bond in 3 dimensions. That's essentially what a structural formula is. There are various ways that we can represent it. So we say that there is a full or extended structural formula, And we typically show you in this way first, so you can understand how exactly the atoms bond. But we can then go into some shortcut methods. We can write a condensed structural formula, and we can even further condense it to form what we call a skeletal formula. To have a look at that, I'm just going to show you a particular alkane, which is butane. This is its molecular formula. It'll have an empirical formula of C2H5. That doesn't really tell us how these atoms bond, so the structural formula shows us exactly how this occurs. Keep in mind that with a structural formula, especially when we get to larger molecules, we generally simplify it by showing the carbon bonds as being flat. In reality, we know that's not the case, but it just makes it easy for us to actually draw these and represent them. And it's widely accepted to represent a structural formula in this form. What we can see here are the individual carbons. We can see that each carbon has 4 covalent bonds. We can see what exactly each of those atoms are bonded to. So this is what we call the full or extended structural formula. What we can then see is each of these contain a certain number of hydrogens or carbon to hydrogen bonds. So we normally like to condense that to just simplify the process and make it easier for us to represent them. So we have a few representations of the condensed formula. Over in this case, we've only shown the carbon to carbon bonds, which you can think of as the more important bonds. And then we've just grouped the hydrogens on each of those carbons. So 3 on the first carbon here, 2 in the second and third, and then again 3 on that last one. Sometimes you might not even show the bond between the carbon atoms. So we can still show that each carbon is made up of, in this case, 3 hydrogens here. The next carbon is made up of 2, next one 2, and then the next one 3. And if we want to further condense that down, then normally when we get to really big hydrocarbons and very big organic molecules, then we often see some groups repeating. So these 2 CH2 groups we can condense by putting them in brackets, and then outside the bracket we can put a 2 here just to show that there's 2 groups within either end of the chain itself. The final way we can represent a structural formula, and it's what I find to be perhaps the most useful for visualizing what these molecules look like in 3 dimensions, it's the skeletal form. A skeletal formula generally only shows the bonds between the carbon atoms, as well as any other important groups, which we call functional groups. It doesn't even show the atoms themselves, but essentially every point here represents a carbon atom. We hide all the hydrogen to carbon bonds as well, and I'll show you how you can determine that. So remember that each of these points is a carbon atom. We can see already the bonds between the carbons. So this carbon is bonded to this one here. This one in the middle is bonded to 2 carbons, and so on. So we know carbon wants to form 4 covalent bonds, and that then allows us to work out what other atoms it's bonded to. So this first carbon here, we can only see 1 bond, which means it needs another 3. The second one, we only show 2, so it needs another 2 bonds. The third one's the same as the second, and the end one over to the right only has 1 bond shown, which is to a carbon, so it would have 3 other bonds to hydrogens, and we can just pop them in. So if we make a comparison between the skeletal and the full structural formula, you can see it shows exactly the same information. This carbon with 3 hydrogens, the second with 2 hydrogens, next with 2, and then the last one with 3 hydrogens. The difference being is that the skeletal form, like I said before, shows you more how these atoms bond in 3 dimensions. So whenever we construct these molecules, we find that they form this somewhat zigzag pattern. This zigzag pattern essentially shows the backbone of the molecule, which is made up of primarily carbon atoms.